So in this slide we are going to discuss a few questions related to TCP, go back N, etc. protocols that we have studied. So question 1 is the following questions related to finite state machine. For the go back N, you have to answer the following questions given M is equals to 6. Now sending machine is in ready state, SF is equals to 10. SF is the first outstanding byte, that is the protocol wants to send the next byte, and SN is 15. So SN is the next byte that protocol wants to send, and SF is the first outstanding byte for which the protocol is waiting to receive the acknowledgement. Let me draw something so that it will be clear to you. Now given value of SF is 10 and value of SN is 9. Suppose let's consider this was the window, and if I say like these are the 3 packets, so these let's suppose many packets. Now this point which is the first outstanding byte, so this point is actually what do you call SF, this point, and this point where next byte is to send, this is SN, this was SF. So out for all these packets, this was sent by the sender, but the acknowledgement has not been received. So value of SF is given to be 10 and SN is given 15. So what is the sequence number of next packet to send? So next packet to send is this one, which is 15. So answer is 15. Second question. So sending machine is in ready state, SF is 10, SN is 15. Now a timeout occurs. So this next byte user will be sending. These are all already sent, and a timeout occurs. So how many packets are to be resent? So in a go back N protocol, all these packets will be resent. So from 10 to 14, all the packets would be resent. So this is the answer. Next question is sending machine is in ready state with SF is equals to 10 and SN equal to 15. Acknowledgement 13 arrives. So acknowledgement 13 means for byte number 12, acknowledgement number is 13. So for this acknowledgement 13 is arriving, that means 13 and 14 are remaining because this was 15. 15 is yet to be sent. 15 is yet to be sent. So remaining would be 13 and 14. So the sender is waiting for 13 and 14th acknowledgement for 13th and 14th segment, right? So 13, so SF would be 13. So SF would be shifted from here 10 to 13, and SN would be exactly same. Now next question is sending machine is in blocking state, SF is 14, SN is 21. What is the size of the window? Now SF is 14 and SN is 21. Now question says it's a go back N protocol with M is equals to 6. So for go back N, if you see for a stop and wait, if it's a stop and wait protocol, sender window is 1, receiver window is 1. For go back N, sender window is 2 to the power M minus 1 and receiver window is 1. And for selective repeat, both the windows are 2 to the power M by 2. Okay, now the value of M is 6, so 2 to the power 6 is 64 minus 1, which is 63. Okay, so maximum size of window is 63 here. Okay, and here because next byte to be sent is 21 and 14 is the first outstanding byte, so distance between them would be 21 minus 14, which would be 7 bytes. So 7 bytes are already sent, okay, and waiting for the acknowledgement. Okay, let's move on to the next question. So sending machine is in blocking state, SF is equals to 14, SN 21, 18 arrives, which is for segment number 17. Okay, what is the next value of SF and SN? So SF would be 18 because 18 byte it wants to acknowledged for, okay, and SN equal to 21. So next state would be ready state because now sender is able to, it's not in the blocking state and it will be in ready state, it can send more bytes. Now a receiving machine is ready with a ready state with Rn equal to 16. Rn is the receiver window. Okay. A packet with the sequence number 16 arrives. What is the next sequence number? So if receiver window, this was a receiver window, this packet was 16, and if this packet arrives, it will move on to next packet, which is this one. So Rn would increment by 1. Okay. So message is delivered and acknowledgement number 17 is sent. So Rn would be 17 and acknowledgement number for this 16. For 16th segment, acknowledgement number would be 16 plus 1, that is 17. So if 16 is coming to you, you sent an acknowledgement number of 17, right? So for 16 byte, it will send acknowledgement number of 17 and it will increment the Rn from 16 to 17. Okay. Next question. Now stop and wait protocol, value of R is given to you 1 Mbps. 1 bit takes 20 milliseconds to make a round trip. What is the bandwidth delay product? Bandwidth into delay. If the system data frames are 1000 bit length, what is the utilization percentage? Now question is A part. Now so question was bandwidth 1 Mbps, system bandwidth is given 1 Mbps and it takes 1 bit takes to 20 millisecond. So bandwidth cross delay, and 1000 bits would take 1000 into 20 millisecond, right? So total time by if I draw it, I would say like, okay, so question was bandwidth delay product. Now 2000 bandwidth cross delay would be 1 Mbps cross 20 millisecond. So 1 Mbps, 1 Mbps is, I'm so sorry, so 1 Mbps cross 20 milliseconds, which is equals to 1 into 10 to the power 6 into 20 into 10 to the power minus 3. Right? So 1 into 10 to the power 6 is 1 Mbps and 20 milliseconds is 20 into 10 to the power minus 3. So bandwidth cross delay. Now utilization percentage. So how do you calculate this? So value of this final answer is you can calculate 20,000, right? And for the second part, final answer is link utilization. Now link is sending 1000 bits only while it could send 20,000. So utilization would be 1000 by 20,000, right? So which is 1 by 20. Okay, so that is 1 divided by 20. So final answer is 1 by 20. Link utilization is very low. Now what if it could send 15 frame sequence? Now if it could send 15 frame sequence, so answer would be, now it would send 15,000 bits, right? So 15,000 divided by 20,000. So that would be 15 by 20. 15 by 20. So utilization percentage increased when we increase the window size from 1 to 15. Okay. Next question. MSS is given to you and find how long it takes to transmit the file. Now assume that 66 bytes of headers are added to each segment before resulting packet is sent to 10 Mbps link. Okay, now bandwidth is given to you is 10 Mbps. MSS is 1460. If you draw it, MSS is 1460 and bandwidth, how much is the bandwidth? 10 Mbps. So R is given to you is 10 M, capital M, BPS, right? Megabits per second. Now what is given to you? 66 bit header, 66 byte header. Okay. Now you have what is the maximum value of L such that all TCP sequence numbers are not exhausted. So how many TCP sequence numbers are there? Because sequence number field is 32 bit. So total is sequence number कितने होंगे? Sequence numbers would be 2 to the power 32. So solution, here is a solution. 2 to the power 32 possible sequence numbers. Now number of segments would be 2 to the power 32 by 1460. So total maximum segments out of 2 to the power 32 bytes, maximum you could have 2 to the power 32 bytes, and each segment is maximum of 1460. So how many segments? So total number of segments would be, number of segments is 2941758 if you calculate, right? Now in each segment 66 bytes of header is added, so this multiply by 66. So total size of header plus data was 2 to the power 32. So 2 to the power 32 plus this number of segments into header. So this is the byte taken by total headers, and this is the total amount of data that you can transmit. So total this much number of bits you can transmit. And how much time would be so for 1 second, in 1 second you can transfer 10 Mbps. So how many bits you can transfer in this much, how much time would it take to transfer this much bits? So you can calculate, right? Next question is a system uses stop and wait if packet carries 1000 bits of data. How long does it takes to send 1 million bits of data if the distance between sender and receiver? Now receiver, so this is propagation distance and time. So D by S is given to you, so which is kilometer by speed. So this is propagation time you can calculate. Now question is if the packet carries 1000 bits of data, how long does it takes to carry 1 million bits of data? Now question is if the packet carries solution is this. So data transmission time is this 1000 bits by this. So for sending 1 million bits, total transmission time would be 1000 bits by 10 to the power 6 bits, which is 1 millisecond. And what is one RTT? So for 1 RTT, total propagation speed is distance upon speed, so which is propagation delay. So propagation time is 5000 km by 20,000, which is 25 millisecond. Now first is in stop and wait, it will send the data. If you draw a stop and wait, so first sender is sending the data, right? Then what happens is receiver will receive the data, right? So they send the acknowledgement. So total time would be this much, right? So this is transmission time. यहाँ पे it would be having this much. So this would be d by s, and this would be again d by s, distance upon speed, propagation time, right? So transmission time, acknowledgement. Now transmission time over here plus propagation time, then transmission time over here plus propagation time. So transmission time over here was this much 1 millisecond, this is 25 millisecond, then 25 millisecond. Transmission time of acknowledgement frame is approximately 0. So So total time would be 1 plus 25 plus 25, so 51 seconds. Total delay would be 51. Similarly, in go back n, window size was 7. So for 7, actually what will have in go back n, it will send the 7 frames. So transmission time 25 into 7, and then acknowledgement. So in the worst case, what will happen is, now transmission time for one window would be 7000 by this. So this is 7 millisecond, like it was 1 millisecond and for one transmission. So because you are sending 7 frames at a time, so 7 into 1 millisecond, so it's 7 millisecond. Now data frame trip time, so this is again for 25 seconds, so 25 per second, 25, 25, 25 and so on. So 25 for one round trip time was 25, so 25 into 7. Okay, now what will happen if it is sending acknowledgement for all 7 at once? So how much? So acknowledgement transmission time was 0, acknowledgement trip time would be 25 milliseconds. So delay for one window would be how much? So 7 millisecond plus 25 plus 25. So total delay would be 57 milliseconds. So in the worst case, full window size of 7 and then wait for acknowledgement for the whole window. Okay, so we need to send this 143 window. We ignore the overhead. Due to header and trailer. Now we need to send okay, data frame transcript time. Okay, what happens is it is sending all the 7 bits at once. Oh, I'm so sorry. So actually this was like this. So this was like this. So sender was sending something. So 7 frames it has sent. Okay. Now it's waiting for the acknowledgement. So it has sent the acknowledgement. So this is 25 plus 25. Acknowledgement for all the frames, okay, at once. 25 plus 25 plus transmission time here was 7. In previous one it was 1. So 7 plus 25 plus 25. Okay. Now in case of selective repeat, what happens is transmission time for 4000 bits. So window size is 4. Okay, window size m would be 2 to the power m by 2. So which is 2 to the power m by 2, which is equals to 2 to the power 4 by 2, which is 4. Okay. So size is 4000 bits by this. So 4 millisecond is the transmission time. Frame trip time would be 25 millisecond. Again, acknowledgement transmission time is 0. So whatever transmission time was there, it was 0. Now 25 is there. So total would be 4 plus 25 plus 25. So this is, that's it.